say entire screen. I said share one
You got
screen.
it. It's perfect.
What are you seeing? Just about me? Is that all you're seeing?
Yep.
See
Yeah.
that? It's perfect. About me. Wow, it's all about you, Mr.
yeah.
Wright.
So this is all
my
about
It's
me.
all about you. Yep.
Where
You
have I
betcha.
heard about? Where have I heard that?
You should have put it all right above it. Yeah.
So anyway, we'll get into the driving robots on Mars bit in just a second. But since you guys are early in your lives, I'll tell you a little bit my early life, and then you can think about it. So,
Oh, we're starting.
What?
We're starting.
We're starting. Hey, if anybody's late, too bad for them.
He needs no introduction. Is that what we're saying?
He needs
That's right.
no
You don't need
introduction.
any introduction. I'm introducing.
No argument.
He needs introduction.
So-
Mr. John Wright. Bada bing, bada bang.
So basically, my family has always been into college and stuff like that. So I was born while my parents were going to Purdue, and my mother has her master's in math from the University of New Mexico. My father has his master's in civil engineering from Purdue.
Smart man.
And my sister, of course, has 5 degrees, and she's a law professor now.
Oh my God.
She decided that school was much better than working for a living. And I pretty much have to agree. Being in school is really a good place to be. Some of you might be thinking, I doubt that any of you guys are thinking that you don't really want to go to college, but you're probably thinking about jobs and things like that. I just want to tell you, stay in school.
Be smart.
Because you will never again in your life be around that many attractive single people. Okay?
Uh-oh.
Word to the wise.
It's ready, G, please.
Yes.
Good morning, Mr. Cuenca.
Good morning.
Morning.
Good morning.
All right. So, still pretty early years. We moved to New Mexico when I was 5, and basically I grew up in Santa Fe, New Mexico. I went to all public schools. I had a 3.58 GPA, but I took all these advanced classes, and back in my day, you didn't get extra points on your GPA for taking the hard things. So you guys are pretty lucky. But yeah, I took all this fun stuff because basically that's what I wanted to do.
And that's on a scale of 4. That's just that there was no 5 scale, right?
That's right. No 5s. You only got 4.
Yeah, there you go. Just making sure you tell them that.
Yep. So when I went to school, I got my bachelor's in chemical engineering from Purdue University because I really liked chemistry when I was in high school. But after 4 years of chemical engineering, I really enjoyed the engineering part and didn't like the chemistry anymore. So I decided to attend bar and have some fun for a couple of years.
That's chemistry.
I really thought the computer science was the way to go. I really enjoyed that a lot more than chemistry. So I went back to school. I was living in Dayton, Ohio at the time, so Wright State was there, and I went back to school. I took a year of prerequisites and then 2 years of classes and a year of working on my thesis to get my master's. And of course, I also worked for the department teaching various classes and labs and things like that, so that helped pay for it. And of course, I took while I was doing my thesis, I didn't have to take real classes, and the university was paying for it. So I took 2 quarters of basketball and 2 quarters of softball and 2 quarters of tennis and some other fun classes. So don't be afraid to have fun while you're in school, okay? Especially with all the attractive single people around there. Okay, so then I finally graduated, probably didn't graduate before your parents were born, but I probably started school before some of your parents were born. So I spent 9 years working at Hughes Aircraft on flight simulators, visualization, image generation algorithms based on voxels, which are like pixels, only they're volume elements. In Texas. I was not real keen on going to Texas, so I got a job at JPL, and I've been working on a variety of things, mostly Mars missions, including Pathfinder, exploration rovers, and the science laboratory missions. All right. So that is the end of that one. Now we'll switch to this one. Where's my little thingy? There it is. Okay. So, one of the things in my life was I never picked up any sports of my own. I always did sports that my girlfriends liked. And so I learned to windsurf when I met my wife because she was a windsurfer. And so after a while of windsurfing and driving robots on Mars, I kind of decided, well, how are they similar and how are they different? Well, they're almost exactly the same. Everything on the left side's all the similarities, everything on the right side's the differences, and you can see they're pretty much identical. But we'll go into a little more detail about that. Basically,
yeah, Right. Can I kick off for a second?
Oh.
On our side, the screen looks kind of weird. I think that you have a dual monitor setup, right?
I got 3 monitors.
Oh boy.
There's a lot of screen tearing. So like
Yeah.
we see like the previous slide like kind of superimposed on this one, and it's
All
really
right.
strange.
Let's see what I can do. If I
Are you
can-
screen sharing or are you sharing an application? Because I think if you share an
just the
application,
application? I'll
Yeah.
stop sharing and then we'll go back to sharing and see. It says a window.
Yes. Yeah,
So a window would be that one.
there we go.
yep, that looks good.
That was
Okay.
better?
Yep.
Yeah.
Okay, good. All right. Just to remind you, everything's the same, hardly anything's different. Okay, so one of the important things is that every kilo, that's kilogram, not kilometer, every kilo matters. So for rovers, we use aluminum components for most of it. I know Pratik wants to use composites, but composites don't really work that well in space because they outgas in the vacuum and they'll deposit organics on other materials and things like that. So we tend to use aluminum. We've also used some titanium stuff. Titanium is more brittle though, so you can't use it for things that bear weight. They had used titanium gears in the arm on the MSL rover, and they kept breaking them until eventually they were able to switch to steel gears and use steel gears, and those don't break, but you've got more weight. So we have strict weight budgets because it costs a lot of money to put even an ounce into space. Similarly, on the right-hand side, when you're windsurfing, you like to use, here we can use organics and things, fiberglass and carbon fibers and stuff like that. We use very thin monofilm for our sails. We have boards made of things like Kevlar or carbon fibers and things like that. So these are the lighter they are, of course, the more expensive they are, that also fits with space stuff. All right, one of the mantras at NASA is test what you fly what you test. So we test our rovers that we build, we test the spacecraft in all sorts of different ways before we launch it. Similarly, we test the carbon fiber mass, that's what you see at the top, before we go flying with our windsurfing equipment. And it's always easier to get off the ground than it is to get back onto the ground. So you can see here, we've taking off of the rocket generally is pretty easy, but they call it that 7 minutes of terror when you're coming in for landing because it's really scary because we don't know what's going to happen. And a lot of times we have no radio signal to tell us what's going on during that time. And you can see here a couple of windsurfers jumping in the air. The one on the lower right, that's my wife. She's a shred Betty. Now, this is the one difference I mentioned at the top, Sherpas. So for rovers, we have a launch team, gets them ready. We have an ATLO team that gets them loaded up onto the rocket. We got a launch team to send them on their way. We got a cruise team to take care of getting them there. We have an entry, descent, and landing team to get it down through the atmosphere. We've got an impact through egress team, and that's just to drive it off the lander onto the ground. Once they finally got on the ground, then we drive it away. If you're windsurfing, you got to carry your gear the whole way down to the water. All right, so sleep or go windsurfing while the rover's busy. We come into work when the rover's done, and it's sent down to Earth the information on what it did and what pictures it took and things like that. We analyze that. We ask the scientists what they want to do. We work out a plan for that. We then figure out how to make the rover do it, and then we go back to sleep. So there are a variety of constraints and issues that are involved here. One is the rovers on Mars are autonomous. They drive themselves. We don't drive them. We tell them what we want them to do, but they go about the business of doing it, and they're not talking to us while they're doing it. So we give them the commands in the morning, then they go about their business in the afternoon, they send the results home and say, this is what happened. All right, so basically, they send us the results, and then between that time and the time they wake up the next morning, we got to do all this stuff. Figure out what's the state of the rover now. If there are any problems, we got to analyze those. We got to analyze the terrain around the rover. We got to figure out what's going on with it, what the scientists want to do, figure out whether it can be done, figure out what the command sequences are to do it, prove them right, and then finally get them ready for uplink to the rover. So that's every single sol. Now, a sol is a Martian day, which is 24 hours and 40 minutes long. So basically, we're sleeping during the Martian day. And the Martian day, because you can see, is not exactly the same as an Earth day. Sometimes it's Martian day during the day here, and sometimes it's Martian day during the night here. So we have a number of programs that we use. The system that we use for building command sequences to drive the rover and operate the arm is called RSVP, Rover Sequencing and Visualization Program. And it's this distributed system with multiple applications hanging off a central message passing thing. So there's a component called ROSE, the Rover Sequence Editor, which basically is what we use to build the command sequences, partly to verify things like, are the arguments for, are they within range, things like that. You can't turn on certain things at certain values and things like that. So it has a lot of range checking in there to verify that things are right. And it basically is the master, it keeps the master copy of the command sequences that we're going to be sending. So if you can see my cursor, this column is the actual command. We have the arguments here, and we have comments over here. If we run simulations on this, this would be the time that we expect that command to execute. This is the command sequence that the command is in, so we can send up multiple sequences. We have this component called hyperdrive. This is our 3D, basically gaming engine, gaming platform, video game type tool. We visualize everything in 3 dimensions. We can move the rover around. We can see how it interacts with the terrains. We can simulate the rover's behavior based on the commands that we're sending it up, and we can play back those simulations as a movie. And so this is what it looks like. You can see here we've got a terrain model for the area around the rover. We've built a path along here. These little lawn darts represent waypoints that we're going to. The yellow thing represents a turn. We're going to turn, when we get here, we're going to turn to face this waypoint. When we get here, we'll turn to face this next one. And then we have tracks, and you can see that they go up and down and bump along as they go over the ground. We have an image browser that displays the images. There's a question, is RSVP an in-house software tool? The answer is absolutely yes. Developed at JPL. It started out as the rover control workstation for the Mars Pathfinder mission for operating Sojourner, and then basically kind of got rebuilt for Mars exploration rovers and rebuilt again for MSL, and they're rebuilding it again for the 2020 rover that's on its way right now. So the image browser gives us, oh, what language does it use? That's a question for you, for me, I guess. So language. All right. So there's multiple definitions of language and use. So I will say that the executive and rows are written, see on the screen, gets boiled down to that digital format to be sent up to the rover. That's one of the things that happens at the end of the day before it goes up. All right. So there are sensors all over the rover. Besides cameras, we've got all these various sensors. We've got inertial sensors and tilt sensors. Oh, what are those? That's that little thing that sits on top of the whatever a robot CPU is. What's the name of it? Anyway, yeah, the Robo Rio. So you got that little board that sits on top of the Robo Rio. It's got gyros and tilt sensors in there. And that's exactly what we use, only ours cost a hell of a lot more.
Okay.
All right. We can drive and use it for, I don't know, 20, 30 hours before it drifts 3 or 4 degrees. Whereas the ones we have on the Robo Rio drift probably a degree a minute, something like that. So they're much more precise and so on. So we have all these, we have sensors all over it. We have encoders on every single joint. We also have resolvers, which are potentiometers. They're not as accurate as the encoders, but they'll give you a value if the encoder for some reason breaks or loses track of where it is. You can reset it using the resolvers. All right. So we figure out what happened yesterday. We've got a whole bunch of ways of looking at it. We study anomalies and problems. Scientists look at the data that came back from the science instruments. We don't bother looking at that. That's what scientists are for. And generally, we are ready to go within a couple of hours of getting the data down. We see presentations that look like this. This is what I was starting to get trained on when I first started working on the rovers. I'd worked on the RSVP software for several years before this, but when I was actually getting ready to do operations, I started on this, which is the downlink side, analyzing the downlink, and they showed me this is one of 5 pages that look like this. And I just said, this is ghastly. The only thing you can tell is that there's a red spot in there, so obviously something's wrong. You have no idea what. So part of RSVP has the telemetry playback window, so you can see the plots of all of that data over time. And when you're doing playbacks or simulations, you can see basically the same. It looks the same, and so you can do comparisons of what you simulated the rover was going to do and what the rover really did. And we get pictures, of course, and look at them. And there's a very, very serious problem on this that was almost mission ending. And I'll show you what it was. There's a rock that got caught in the wheel. So when the wheel dug down into the soft soil here, there was a rock right next to it, and it kind of fell in. And as we started to drive, it twisted around and jammed in between the hub and the wheel. Now, fortunately, we were able to turn the wheel the other way and unjam it and then kind of wiggle our way away from the rock and drive away. So it did not fatally end the mission. Now, let's see if this is going to work. It says I can play. Let's see if it'll play. Playing. Oh, does it say media not found? Oh, yeah, it does. Okay. So anyway, this is actually a comparison of the actual drive and the artificial drive or simulated drive. And it turned out the simulated drive, of course, just goes whoosh right over here to the end. The actual drive came right up here and stopped. And the reason it stopped was because from this waypoint on, we used autonomous hazard avoidance. So the rover has multiple driving modes. One of them is just blind, where it just drives. Another one is called VO, visual odometry. What it does is it drives a step, takes an image of the ground, drives a step, takes another image of the ground, and then it tracks rocks and features in the images and compares them, looks at to figure out where it moved. And that allows it to compute how much it slips. Okay? And so slippage is important because anytime you're on any kind of a tilt, up or sideways, the rover is going to slip. And so using visual odometry allows you to compensate for that. There's another mode called auto where it just says, oh, I will drive for a while, and then I'll use my visual odometry for a couple of steps to see if I'm stuck. And if I'm not stuck, I'll turn it off and just keep driving. And then the fourth mode is autonomous. Actually, there's a guarded mode, which says I'm going to drive forward, and if there's anything hazardous in front of me, I'll stop. And then there's auto nav mode, where it says I'm going to drive, but if I see something hazardous in front of me, I'll try to figure a route around it, and it'll try and dodge around it. So in this particular case, we were right in here using autonomous auto nav mode, and said, oh, there's something in front of me. So it backed up and it tried to go around it. And you can see in the playback that it actually tries to dodge around something. And then finally it runs out of time and it gives up. So there was a question about when was RML developed. So RML was developed for the Mars Exploration Rover mission. And it's just a hyperdrive markup language variant for specifically designed for our rovers to support all of the commanding, and it stores a bunch of other relevant information, such as the terrain models we were using for our simulation and modeling. It uses the initial conditions of the rover. We have to know where the rover is, what's going on with it, things like that. And all that gets stored in the RML files. All right, so we get a list of what we want to do today. So there's a high-level activity plan. This is a very tiny little snapshot, but the real activity plan is like 100 megabytes or something like that. It's just pretty much nonsense as far as I can tell. But anyway, we now, Yasmin, for those of you who remember Yasmin, she wrote software to pull the important stuff out of those gigantic activity plans and ingest them into RSVP so we can use them to initialize our sequences for the day. One of the important things for both windsurfing and driving on Mars is the weather. So on Mars, we have dust storms. They come up every few years, and I think they're linked to sunspot cycles. And we get these dust storms. You can see here, basically this is what's called, we have tau. Blue is tau. Tau is basically a measure of how thick the atmosphere is. And actually, it's the other way around, I think. Tau is, if it's thin, it's higher. And then this is how much power we're getting on the solar panels. So as you can see, this power drops when the tau goes up. And then here, we can see we had a really bad tau here. And that's this dust storm over here, and the power dropped very, very low. Fortunately, it was not so low that it died. But eventually, Opportunity died when there was such a bad dust storm that it didn't get enough power to keep itself going at all. And let's see. Yep. So this is kind of what it looked like from the orbiter. So you can see all the detail on the ground when there wasn't much of a dust storm, but about 3 or 4 weeks later, you can't see hardly anything on the ground because the dust in the atmosphere is so thick. And that's what it looked like from the ground, with the tau level going from 0.94 up to 4.7. Now, Curiosity is nuclear powered, so it doesn't care much about the dust. So, for both rovers and windsurfing, spring winds are our friends. Springtime, the wind comes up. We all go to the beach and go windsurfing because the wind tends to be nuking then. We get these, this is what happens on our rovers though. You can see these little bumps. When springtime comes along, the wind comes up and it blows the dust off the solar panels. So as the dust builds up during the winter, the power level goes down and down and down. Then eventually spring comes around and we start getting these little puffs of wind and it blows the dust off and our power level shoots back up. This 845 is almost a totally clean solar array. So that's a nice thing for us. These are the kinds of wind charts we see for windsurfing in Seal Beach in May. You can see here it's averaging 20 miles an hour with gusts up to 26 or so. So that's really good windsurfing. Here you can see down in the lower left, dusty solar panels versus shiny, clean solar panels. All right, so let's talk about the cameras and stuff on the rover. So most of them, I should say, are stereo pairs. This is on MER, but most of the rovers tend to have similar kinds of cameras. We have HAZCAMs, those are hazard avoidance cameras. Those are stereo cameras located front and rear down low. We have the navigational cameras, NavCams, which are up on the mast. They have about a 45-degree field of view. The HAZCAMs actually have a 180-degree field of view or more from corner to corner, so they're fisheye lenses. And then on MER, we have what are called PANCAMs, panchromatic or panoramic cameras, but I think panchromatic is better. And there's actually a color wheel inside this little round thing, so each camera can take a different color. And there's 8 different colors in each of them, and they're not the same in either ones. And so they can't take red, green, and blue because they don't have red. They actually take an infrared, near infrared, and green and blue, and they'll put that together and they'll call that a color image. On Curiosity, we have what are called the mass cams, and they're even higher resolution. They're built by a company down in San Diego called Malin Space Science Systems, and they're operated by the science team. And they're also, again, stereo pair, but they have different fields of view on the left and the right, so they're kind of weird. So when we do these, we take images left and right. So you can see here we've got looking out at the landing site of Spirit on MER. And you notice the right's on the left and the left's on the right. So if you're good enough, you can cross your eyes and see 3D. I can do it quite easily, but I have years and years of practice. So anyway, and these round marks back here, those are actually the airbags. When Spirit and Opportunity landed, they were in airbags, and they bounced along before coming to stop. So these are airbag bounce marks. So there are a couple of questions. How much power is required to keep the rover alive? It's actually absolute minimum is somewhere around 80 watt hours, something like that. It's not a lot. The real important thing, you can shut the entire rover down, but what'll happen is it'll get so cold that the electronics boards in there will shrink and then they'll crack, and that will basically kill the rover. So you have to keep a certain amount of heat in there just to keep it slightly warm so that they don't break. And so those survival heaters are basically the last thing to go. Another question was, is there any moisture acting on the dust layer? And the answer is no, there's very, very little moisture in the atmosphere on Mars. There's ice buried under near the polar ice caps, buried under dust. Occasionally, we do cloud surveys on a reasonably regular basis, but I'm not sure if maybe once we saw some slight puff of a cloud. So generally, there's no moisture in the atmosphere. So the dust, it'll build up, but it just tends to stay very light and not sticky. The only thing that sticks it on there is going to be static electricity. So we have to deal with that, but we don't have to deal with moisture packing it on there or making it really stick. All right, so here we build our 3D terrain models. This is Spirit's landing site. So this is like one of the first models we built after we drove off the rover. And of course, there's a big hole. You can see there's a hole right here in our mesh because the rover can't see underneath itself. So that's there's just a hole in our terrain model there. This stuff is either some of this like this is probably a little ridge that we can't see over. This is the lander. So we actually came down on this and drove off. This is what it looks like from down from a lower view in hyperdrive. This is the underlying wireframe mesh. So it's a texture mapped mesh. And multi-resolution with automatic switching of different resolution levels as you move around within the terrain. This is what it looks like from a fairly low point of view. This is us approaching a rock. I think that's the rock called Jake Matijevich. I'm not sure. Looks like it. And it's a model of us putting the instrument on to the rock. No, it's not Jake Matijevich. That's totally wrong. All right. So basically, we have to build command sequences to operate the rovers. And to do that, we bundle them into these commands are bundled into sequences. The sequences basically are like functions or subroutines. If you write software, you know what those are. And we'll have a number of those. There's a master, and then it calls all the subsequences in the right order, the right time. And those call additional subsequences and things like that. We can run them in serial or parallel. You can't run more than 16 at a time. And you can't have recursion or looping. There's no iterations. We don't have any constructs like that in the rover commanding language. But we do have conditionals, and you can call a subsequence as many times as you want rather than looping it. So here's our commands. You can see these happen to be the commands. These should be the commands that, so these right here are drive commands. You tell it how far to drive, how much to turn. Do you want to have auto nav hazard avoidance on or off, things like that. These various arguments tell it to do that. All right, so we have to prove that these sequences are right. So we have walkthroughs, 2 a day. We actually walk through all the commands. Certainly the rover planners, that's what I am. We're called rover planners, not rover drivers, because rover planner sounds really boring, and that cuts down on the competition for the job. But the rover planners have to walk through our sequences. We're responsible for all the driving and all the arm motion, and basically those are the only things that can really damage the rover. So we have to prove our stuff is correct. So we have these walkthroughs. We walk through the code. We play back the animations for everybody to look at, make sure we're doing the right thing. We have our simulations that use flight software to model what's going to happen. If it's something that we've never done before, we'll run it through software that will simulate it in a much more detailed flight software simulation. And if it's really something that we're worried about, we can have a rover on our test bed that we can run it on as well. We have to document everything with reports and simulation files and animations and things like that. And we have all these meetings during the day to do all the various purposes. The SOG meeting is where we discuss what we're going to do. The activity plan is, there we go. The activity plan is where we've worked out what the activities are going to be, and if the power and all that's the constraints and everything are met, then we've the master submasters where we walk through our sequence the first time, and command approvals we walk through it the second time. All right, so I don't know if this one can find the media. Let's see, what's it say? It says media not found. Okay, so this is a drive. The only interesting thing really about this drive is all this stuff, red stuff right in here. This is a bunch of turns. Now, the rover doesn't have a shovel on it, so it doesn't dig. But if you want to see what's under the ground, what we do is we actually use the wheels. So in this particular case, we're driving along this little dust dune right here. So as we drove along it, we would put one wheel through it, and we would then wiggle the wheel back and forth. We'd actually turn the rover back and forth to dig up the dust really well. So and then we came over here and we took a bunch of pictures looking back at it. We also can park, turn one wheel sideways, and then spin it one way, rotate a little bit, spin it the other way, and actually dig trenches. So we use the wheels to dig into the ground rather than any kind of a shovel. All right. So now wind, because there is no dust, I mean, we talked about moisture. There isn't any moisture or water on Mars, certainly not in the last 3 billion years or so. So wind is much more of an effector of the surface of Mars than it is on Earth. So you can see these interesting sand dunes. These upper ones are down in the bottom of a crater. As the wind blows across, you get these eddies of air inside the crater that stirs up these interesting looking dunes. These are sand dunes. We were driving across just a giant plain of dunes that aren't too thick. And of course, waves on Earth affect us a lot. So we deliver our sequences, we do our uplink reports, and we go home to go windsurfing. So our afternoons are for windsurfing. So here's some pictures, just some kind of related pictures. We'll zip through some of these kind of fast. So this is Spirit after it landed. You can see this giant thing right here. That's not a rock, that's an airbag. So Spirit and Opportunity came down on airbags and bounced. And then we tried to pull the airbags in, but we didn't successfully pull this one in enough. So they ended up pulling them in some more, and then they were eventually able to drive off. Fortunately, they just drove off straight forward. This is the rear view. Here's a rock that's in Endurance Crater. You can see all of these tracks. We drove over to it. This is the actual tilt, so there was a lot of slippage in here. So we had to drive very carefully across slope, typically aiming above where we wanted to end up and letting the rover slide down as we drove across. Here's some tracks at Meridiani. Now, remember I was telling you about visual odometry. So if you're driving and you're tracking whether you're slipping or not, you're looking down at rocks and features on the ground. Unfortunately, out here, there aren't any features. There's nothing to track as you're driving. Well, it turns out there are holes in the wheels. There's this special pattern in the wheels, and that was used for to tie downs, cables that tied the rover down to the lander. And the lander, once it landed, there were explosive bolts that cut those cables, so then the rover could stand up and drive off. So it turned out those holes and those marks on the ground, the cameras were able to track those and use those for visual odometry. So we actually drove backwards looking at our tracks as we drove across the ground to track how far, whether we were getting stuck in sand dunes and slipping and things like that. Now, on Curiosity came down underneath a parachute, or underneath with a jetpack actually, and it landed, and so it didn't have a lander to be bolted to, so it didn't have to have these holes in the wheels. But we put holes in the wheels anyway for this specific purpose, just so that we could use them for tracking during visual odometry. And we were going to write the words JPL on there, and NASA said, no, this is not a JPL mission, it's a NASA mission, you can't say JPL. So we said, okay, we'll just put holes in the wheels. So they put holes in the wheels that by some coincidence happen to be Morse code that happens to spell JPL. This was an interesting thing. This was the heat shield from Opportunity. We got to go over and drive and take a look at it. And it's the first time we've ever been able to see a heat shield that had been used in the atmosphere of another planet. So there was a question about why we don't mount a fisheye camera on the underside of the rover. We actually did mount a camera on the underside of Curiosity. And I'm sure there's one on Percy, that's on its way now. But it's not a fisheye, it just kind of was used, they wanted to use it to look down at the ground as it's coming into land. And the main purpose of that was they want to track the ground and see if there are crosswinds blowing them sideways. Then they can use the jetpack to compensate for crosswinds so that they come straight down when they land. There's an interesting thing here. This is another view of it. This is color. Now remember, this is where we used infrared instead of red. So the color is always just a little off. It's not quite what it looks like, but it's close. The interesting thing is that rock on the left side, which is a meteorite. There's meteorites all over. We've seen several of them. All right, so Spirit drove down across started up here at Sol 1 in the upper left-hand corner. We drove over to this first crater. That was boring. So we drove over to the second crater. That was boring. We drove to another crater. That was boring. We finally drove all the way over into the hills over here. These are the Husband Hills. Husband Hill is one we climbed up. Then we drove down here to an area called Home Plate, where we eventually got stuck. There's a picture of us. You can see us from space right there at the top. But eventually we got stuck right here in an area called Troy, and the rover died there, and that was it for the Spirit mission. So one of the important things about lessons we learned from there is it's better to be on top of the surface than underneath. So Spirit got stuck in this very, very soft dust. We built a test bed here on Earth where we put Spirit in and tried to dig our way out. And perhaps unsurprisingly, it was always able to get out from our test bed. But we were not able to get out on Mars, and the mission ended there. Opportunity, that's Opportunity right there. You may think it's this thing. It's not that thing. It's that thing right there. So that's Opportunity on the edge of Victoria Crater, which is a very much larger crater. And this one, finally, we saw interesting stuff. So we ended up we got here, we looked in and we saw some interesting features here, but they wanted to drive down in the crater. So they said, let's look for a good place to drive in. And they drove all the way around here to Sol 1153. And they finally said, the best place to drive in is all the way back here where we first arrived. So we drove all the way back here. We drove down into the crater and we explored a little bit in there. And you can actually see the tracks from space. Those are the tracks of Opportunity. And you can actually tell there's 2 tracks. You can see that from space because our camera is so good and the atmosphere is so thin. And this is what we're looking at. So you can see the layers in the rock, different kinds of layers. Layers are critically important to scientists. Why? Because there's only 3 mechanisms that create layers. One of those is volcanoes. Volcanoes dump out lava. Lava builds up and cools down and hardens, and then maybe it erupts again, some more lava comes and makes another layer. Another way is a volcano erupts and blows out dust or ash, or possibly wind blows dust in and builds up dusty layers. Then the dust sits there and hardens over a few centuries, and then another layer of dust blows in. The third and most interesting way, of course, is water. Water carries sediment down. The sediment is deposited and then maybe dries up. And then 100 years later, some more water comes down. So basically, there was liquid water on Mars. But if they want to look at these layers, because the thickness of the layers will tell them which of those 3 sources caused these layers. So here's some of the area where we were exploring after we left Victoria Crater, which is right there. We drove off down this direction. And this is just this giant plain of dust. And it looks like this with all these little ripples and things. But turns out those ripples are just like waves on Earth. They have a good side and a bad side. One side's firmer than the other. So we tried to stay on the firm side of the ripples, stay between the waves as we're driving across there, and stay on the nice front face of the waves when you're out windsurfing. Same with this. So you can see here, we're coming in, driving mostly parallel to the waves. Then we had to drive off across the waves. So we're trying to find areas with more exposed bedrock. We can see that from space to plan our routes to stay out of, so we don't get stuck. Stay out of the deeper, thicker dunes. This was a couple of different routes. We ended up doing the one on the left. So Mars Science Laboratory is on its way, and that's enough of that. Okay. Did you get your question answered, Alejandro? Why did Spirit die? Spirit died because it got stuck,
Yes.
and then winter came along, and the sun got down at such a low angle in the sky that with the sun being low, the rover being tilted in a little bit in the wrong direction, and the dust buildup, that the power level got low enough that it couldn't keep the survival heaters on, and it died.
So it froze all the circuits.
We don't know. We never heard from it, so we don't know what happened. It just died.
Okay.
And now there's a question. What is the latency for sending commands from Earth to the rovers? So that depends, clearly, on where they are in their orbits. So when Earth and Mars are closest together, its one-way light time is about 4 minutes. So we could send it a command, and then 4 minutes later, it would receive the command, plausibly start executing it, and then 4 minutes later, we would see the results. That's why we don't use joysticks to operate the rovers. Now, of course, if it's on the other side of the sun, it's 20 minutes each way. And that's even harder. It's hard enough just driving something on the moon, which is only about 8 seconds one way. And that's not necessarily the light time. It's also getting through all of the systems that you have to route the signals through and things like that. All right. Any other questions? Hearing stunned silence. I know I have more stuff. I have so much stuff to show. Where is it? There it is.
There's another question.
All right, let's put this up here. You probably can't see it. So we will say, stop sharing, and then we'll share. This one. Okay, so now you see a big black screen. This is an animation. It's sort of playing right now, but somebody asked a question about having a camera on the bottom of the rover, and this is what it's used for. It's called the Mars Descent Imager, or MARDI. You saw the heat shield fall off, so the bottom of the rover is now facing the ground. There's no lander. We're coming in now. We're compensating for crosswinds right there, and then comes down, and there we are on the ground. So there's a question about the sun sending signals a problem, and the answer is yes. It does make a problem. We have a time every year called conjunction. We'll go ahead and play that while I'm talking. And during conjunction, we take about 1 to 2 weeks off. We don't send any real commands. We don't drive. We don't do anything. It's at all risky for the rover. It's not when it's behind the sun, because the odds of Mars and Earth being really exactly on opposite sides of the sun, with the sun itself in the way, is fairly low. But the corona and all of the radiation coming from the sun and things like that, when it's within 2 degrees of the sun, we decide that's risky. We don't send any kind of risky commands. We don't do any driving or anything like that when it's within 2 degrees of the sun. So it gives us a couple weeks off. We work on software, we do other things or we just go on vacation, whatever. All right. One other thing. Let's see, where is it? I have so many things here. All right, so this is actually a video. It's a cutout of the video you just saw, but in this one, we can actually see the heat shield when it hits the ground. So right there, that's the impact of the heat shield on the ground as we're coming down. And we drove over to the heat shield and some other areas. Actually, I have a picture of that as well. Let's see if I can find that one. There it is. All right. So here you can see this is where we landed. This is the called the sky crane, the jet pack, whatever you want to call it. That went over here. So after it dropped MSL to the ground, it flew away and crashed over here and basically exploded. And this is the parachute and the back shell, which is the top part that the rover is hanging underneath. So the heat shield falls off the bottom of that. I'm not even sure it's a heat shield. No, heat shield's not on there. So I'm not sure where the heat shield is. But so this gives you there. And so we actually drove over here to explore this area, and then we headed back this way and down off in this direction to Mount Sharp, which is what we're exploring now. Okay, this is what frequency the antennas use to transmit signals to the rovers. I have no idea. Glad I can answer your question promptly. All right.
I think they may be on X-band.
They use different frequencies, right?
Right.
I think they use X-band for, don't they use X-band for local communication to the satellites and a different band for the high gain antenna that talks directly to Earth?
Yes. So there's X-band and Ka band and K-band. So the X-band, I think, is like from 8 to 10 gigahertz, and Ka-band is like 20 gigahertz, 18 to 20, and then Ka is like 34 gigahertz, 30 to 34. So those are the ones. So I think on one of the Mars missions, we use those small satellites. And those communicated in X-band, but also communicated in Ka-band. So those are the ones that I worked on when it was in Curiosity, InSight, when InSight landed. They used the CubeSats, 2 CubeSats, and they kept the communication shorter for, I think it was less than 4 minutes.
Okay. So Nathan's asking me if we can share any of our fun acronyms, okay?
Yeah.
Well, the best acronym, of course, was Fiddlesticks. That was the Formal Interactive Dynamic Data Flow Language Environment for structuring topological iconosymbologies and configuring knowledge-based systems.
Wow.
And that's exactly what it did, too. I also got a challenge to come up with a set of related acronyms for all the parts of RSVP. So I came up with a bunch of those. The top level was called ARES, Amalgamated Rover Engineering and Science. So they're all Zodiac related. So Zodiac was the Zonal Operations Director for In Situ Activity Commanding. Scorpio was a system for command and overview of rovers in the paradigm of immersive operations. Gemini was the graphical environment for mapping and its in situ navigation information. Let's see, Taurus was the telemetry analysis utility for reviewing unit state. I know there's more. I came up with all 12, but some of them are pretty hard to remember.
Wow.
But you got to come up with acronyms. TLAs, 3-letter acronyms. Okay, it's 12 o'clock.
Wow.
Any other questions?
Pretty cool. Nice presentation.
Thank you. I've done this before. I might as well show you this while we're here. All right, so this is to show you what happens in the spring, right? So you're looking at this. There's nothing out there. We still don't see anything. And then all of a sudden, a dust devil goes blowing through.
Oh, yeah.
So dust devil is one of the interesting things. We actually could see tracks from space, these wandering tracks across some of these dusty areas. And they're actually caused by dust devils blowing across. And this is the sort of thing, if one of these hits the rover, it just goes whoosh and blows all the dust right off the solar panels.
Right.
So these are great. So we do actually have weather on Mars. All right. Guess I can show you this one also.
Hey, John,
Yep.
will you be working on Perseverance?
I am not working on Perseverance. What? A break.
You need a break?
Now I said I can't. You must grant permissions. How do I grant permissions now? Stupid.
Eh,
mm. I don't know. Somehow I turned off my permissions. So now I can't share anything ever again.
Oh, reboot.
Maybe.
What communication protocol do they use for the rovers, like to transmit the data?
I couldn't tell you if my life depended on it. It's magic.
Magic.
Yep. They do some handshaking. There's some encryption on it. There's, I don't know what else. So, any other questions? I heard something.
Yeah. Wasn't me.
Something about targets. Oh, were the moon landings faked?
What?
The answer is probably not.
But
thing is about stuff like that is you'd have to have so many people sworn to secrecy and so many people not letting the cat out of the bag. You don't hear any of the people that really worked on the moon landing saying it was fake. The people that are saying it was faked were people who
we're not.
Yeah, they weren't associated with the mission. And you can't keep a secret. If more than two people know a secret, you can't keep it. It's public. So a lot of these conspiracy theories, you basically, you can just debunk them on that basis. Too many people know, and somebody will spill the beans.
Okay, I think we're done.
All right, then. I guess we're done because I can't share anything anymore.
Well, that's right. You have to reboot.
I guess.
Well, thanks, John. Appreciate it.
Thank you
You're
so
welcome.
much. Thank you so much. Mr. Wright, that was awesome. Appreciate it. All right. Have a go windsurfing.
I
Yeah.
would. I'd like to.
All right. Take care, everybody. Thank
All
you
right.
again.
Thank you.